Hello, my friends. Have you ever looked up at the night sky and wondered about the secrets hiding in the darkness? Well, today we're going on an adventure to explore the most interesting topics in the universe, black holes and their relation with theories of general relativity and quantum mechanics. Imagine a black hole as a giant cosmic vacuum cleaner, so powerful that it sucks in everything around it, even light. But black holes aren't just scary monsters, they're also amazing scientific puzzles. Scientists have two incredible rule books for understanding how the universe works. One book is called General Relativity, and it's really good at explaining big things like stars and planets. The other book is called Quantum Mechanics, and it's perfect for explaining tiny things like atoms and the particles inside them. The problem is, these two rule books don't seem to agree on how black holes should behave. It's like trying to use the instructions for building a spaceship to make a toy car. It just doesn't work. So, scientists are on a mission to figure out if black holes can help them combine these two sets of rules into one super rule book that explains everything in the universe.
Can you explain more about a black hole?
A black hole is a place in space where gravity is so strong that nothing, not even light, can escape. Imagine a giant drain swirling everything down, down, down into a mysterious darkness. That's the power of a black hole.
How do they form?
Well, sometimes giant stars run out of fuel and collapse in on themselves. This creates an incredibly dense object with immense gravity. Anything that gets too close to the edge, called the event horizon, gets sucked in and can never escape.
What's inside a black hole?
That's a mystery even scientists are still trying to solve. The center of a black hole, called the singularity, is where things get really weird. The laws of physics as we know them might not even apply there. It's a place where space and time get twisted and warped, a true enigma in the vast cosmos.
Can you throw more light on general relativity?
Sure. Imagine space as a giant, stretchy trampoline. Now picture a bowling ball placed in the center. What happens? The trampoline bends and curves around the ball, right? That's kind of how Einstein's theory of general relativity works. Instead of a trampoline, imagine space and time as a single, flexible fabric called space-time. Massive objects like planets and stars act like the bowling ball, curving the space-time around them. This curvature is what we experience as gravity. So, when you feel yourself pulled down towards the earth, it's not an invisible force. It's you sliding down the slope created by Earth's mass in space-time. But here's where it gets even more interesting. General relativity also tells us that gravity doesn't just affect objects, it affects time too. Clocks near massive objects actually tick slower than clocks farther away. That's why time passes a tiny bit slower for astronauts in space than it does for us on Earth. Einstein's theory has been incredibly successful at explaining all sorts of things, from the bending of light around stars to the existence of black holes. It's a mind-bending idea, but it's one of the cornerstones of our understanding of the universe.
Great. Now can you explain quantum mechanics?
Let me explain this. Have you ever wondered how the smallest building blocks of our world work? Tiny things like atoms and the particles that make them up. That's where quantum mechanics comes in. In the quantum world, things get a bit weird. Imagine a tiny ball that can be in two places at once, or a cat that's both alive and dead at the same time. This might sound crazy, but it's how quantum mechanics describes the behavior of particles. Quantum mechanics tells us that energy and matter come in tiny packets called quanta. It's like having a box of chocolates, where you can only have a whole chocolate, not half or a quarter. And even more mind-bending, these particles can act like both little balls, particles, and waves, like ripples in a pond. This theory might seem strange, but it's incredibly powerful. It helps us understand things like how atoms work, why the sun shines, and even how lasers work. So even though it's a bit weird, quantum mechanics is essential for understanding the fundamental building blocks of our universe.
Why cannot general relativity and quantum mechanics get along?
Let us understand this. These two superheroes are fantastic at explaining their own domains, but they clash when it comes to the most extreme places in the universe, like inside a black hole. Inside a black hole, gravity is so incredibly strong that it should warp space and time to an infinite degree. This creates a point called a singularity, where the laws of general relativity break down. But quantum mechanics doesn't like infinities. It prefers everything to be quantized, meaning that it comes in discrete, measurable amounts. This clash between the smooth, continuous nature of general relativity and the quantized, discrete nature of quantum mechanics is the heart of the problem. It's like trying to fit a square peg into a round hole. Scientists have been trying to reconcile these two theories for decades, but it's a tough nut to crack. Black holes are the ultimate testing ground for any theory that claims to unify these two. If we can figure out how they work together in these extreme environments, it could lead to a revolution in our understanding of the universe. So, while general relativity and quantum mechanics might not be best friends right now, the hope is that black holes will help them find common ground. Until then, the mystery of how to unify these two powerful theories remains one of the biggest challenges in physics.
Could black holes be the key to unification?
Let us discuss about it. Scientists believe that by studying black holes, they can gain valuable insights into how these two theories might fit together. Black holes could hold the secrets to a new unified theory of physics that explains everything in the universe, from the tiniest particles to the largest structures. It's like using a magnifying glass to examine a tiny insect. By looking at black holes in detail, scientists hope to find clues that will help them unlock the secrets of how gravity and quantum mechanics interact, leading to a deeper understanding of the universe and potentially revolutionizing our knowledge of physics. So, are black holes the key to unifying these two seemingly incompatible theories? It's a question that keeps scientists up at night, but the potential rewards are so great that they're willing to explore every avenue. After all, black holes might just be the missing piece we need to complete the puzzle of the universe. Scientists think that studying black holes could reveal a deeper theory that encompasses both the large-scale universe of gravity and the tiny world of quantum particles. One of the biggest mysteries surrounding black holes is the information paradox. According to QM, information, or the state of a particle, cannot be destroyed. But if a black hole swallows everything, including information, where does that information go? Solving this paradox could lead to a major breakthrough in our understanding of physics. Another mind-boggling puzzle is the firewall paradox. This paradox suggests that the edge of a black hole, called the event horizon, might be a fiery wall of energy that would burn anything that tries to cross it. This contradicts Einstein's theory of general relativity, which says that falling into a black hole should be a smooth experience.
What are scientists doing about it?
Well, string theory suggests that the fundamental building blocks of the universe aren't point-like particles, but rather one-dimensional strings. The way these strings vibrate determines the properties of particles, like their mass and charge. Think of it like a guitar string. Different vibrations create different notes. In string theory, different vibrations of these tiny strings create different particles, like electrons or quarks. What's even more exciting is that string theory naturally incorporates gravity, something that quantum mechanics has struggled with. This makes it a promising candidate for a theory that can finally bring together our understanding of the very big and the very small. Scientists are hard at work exploring the complex mathematics of string theory and looking for ways to test its predictions. It's a challenging and ongoing process, but the potential payoff is huge. If string theory is proven correct, it could revolutionize our understanding of the universe and reveal a deeper, more fundamental reality than we ever imagined. Another theory is known as loop quantum gravity. This theory suggests that space itself isn't continuous, but made up of these tiny building blocks, like pixels on a computer screen. These loops are so small that we can't see them, but they could be the key to understanding how gravity works at the quantum level. Just like Legos can be combined to build all sorts of different structures, these loops of space can connect and interact in various ways to create the fabric of space-time. This could explain how gravity emerges from the quantum world, just like how the picture on your computer screen emerges from millions of tiny pixels. Scientists are working hard to explore the implications of loop quantum gravity. They're using powerful computers to simulate how these loops might behave, and they're looking for ways to test the theory's predictions through experiments and observations. Loop quantum gravity is a complex and challenging theory, but it's a promising avenue for unifying these two theories. If it turns out to be correct, it could revolutionize our understanding of the universe and reveal a deeper, more fundamental reality than we ever imagined. Another approach is black hole thermodynamics. Ever heard the saying, "You can't get something for nothing"? Well, that's a big rule in physics too, especially when it comes to energy. Scientists have noticed something really strange about black holes. They seem to follow similar rules about energy as a cup of hot tea. This might sound weird, but stick with me. When you put ice in hot tea, the tea cools down and the ice melts. Energy from the tea flows into the ice, changing its state. This is what we call thermodynamics, the study of how heat and energy change things. Now, black holes aren't exactly like tea, but they do seem to have a temperature and give off a tiny amount of energy called Hawking radiation. This means they're not just giant vacuum cleaners, they're also kind of like cosmic radiators. By studying this connection between black holes and thermodynamics, scientists are hoping to unlock the secrets of how gravity works at the tiniest level. It's like using the rules of heat and energy to understand the complex dance of particles inside a black hole. This could be a major clue in the quest to finally unite general relativity, the theory of big stuff, with quantum mechanics, the theory of small stuff. So, black holes aren't just terrifying voids in space. They're actually incredible laboratories for testing our understanding of the universe. By looking at them through the lens of thermodynamics, scientists are edging closer to the ultimate goal of physics, a single theory that explains everything. The search continues. While we don't yet have a complete theory that unites GR and QM, black holes are providing us with valuable clues. As scientists continue to study these cosmic giants, we might finally unlock the secrets of the universe and discover a unified theory of everything.
What is the future of physics?
The unification of GR and QM is one of the biggest challenges in modern physics. If scientists succeed, it would revolutionize our understanding of the universe and open up a whole new world of possibilities. But even if we don't find a complete solution, the journey of exploration is pushing the boundaries of human knowledge and revealing the incredible mysteries that lie within the fabric of reality.
If you like this video, please like, comment, and share the video, and please do not forget to subscribe for more videos.